Hi again, Dr. P here, and in this lecture video we'll take a look at the Michael reaction and the Robinson Annulation, which is actually a ring-forming reaction involving a Michael reaction and an Aldol reaction. Alright, so let's start with the Michael reaction. So in general, what happens? Well, we have something that will form an enolate. And we will have an alpha-beta unsaturated species as our electrophile. And we'll go ahead now and we'll form our enolate, and it will add not to the carbonyl but to the beta carbon. Remember, as we've talked about before, this beta carbon is also electrophilic. Remember, a Gilman reagent adds there instead of adding at the carbonyl like a Grignard would. So we can do this in base. Might be able to do it in acid, typically done in base though. And we'll get R, C, double bond O, CH2, new bond. That guy is now CH2, that guy's a CH2, that is C, double bond O, H, like so. We get a 1,5 diketone. Okay, I guess this is an aldehyde and a ketone, but anyway, the diketo species, 1,5 diketone. Trying to make my E's a little more visible there. Alrighty, so this is our new bond between carbons 2 and 3 of our 1,5 diketone. Alright, so let's take a look at the mechanism. The mechanism, of course, starts with the formation of the enolate. So let's have some base here. We'll just use hydroxide. That pulls off that proton, and we will get our enolate forming. Lone pair negative charge. And now we have our conjugate species here, our alpha-beta unsaturated aldehyde in this case. And again, let me label these guys. This is our enolate formation. Now we will have nucleophilic attack. And that occurs at the beta carbon. Now when this happens, of course, let me put in the hydrogens here. H. When this happens, these electrons have to go somewhere. So they're going to go scoot over. And now these electrons in the carbon-oxygen double bond have to go somewhere. So they're going to go up onto the oxygen like so. Alright, and then I'll show you a slightly different way to draw this in just a sec here. So we now have R, C, double bond O, C, H, C, H, C, H, C, O, minus H. Now, this could pull a proton off of something and make an enol, or if we had our water here, how do I know I have water? Well, I just made it back here. I could actually get these electrons kicking back down and those pulling off there. And that gives us now R, C, double bond O, CH2, CH2, sorry, ran out of space there. Gives me my final product here. All right. Now, I could have drawn this step a little different. This last step here is a proton transfer. And you may have noticed that I screwed things up here with this. It's a little late in the day, so I'm going to blame it on. I screwed things up there. I need to pull off my proton, not attack my oxygen. That's just crazy talk. An alternate version which may be a little easier to keep track of involves our enolate adding to the beta carbon, and then those electrons being pushed up onto the alpha carbon. So that we now have R, C, double bond O, C, H, H, C, H, H, C, negative charge, H, C, double bond O, H. And then we'll get our proton transfer. Those lone pair will pick up that. So you don't have to show the electrons being pushed up onto the oxygen here. Again, that's kind of the way I think when I think about things. I think about these electrons flowing around back and forth. And if you want to draw it a little more directly like this, remember, this version of the enolate is one of the resonance structures. So when you actually get to this step, this and that are resonance structures. And I mean, technically you should actually probably draw both of them, but the key here is that when you do the final proton transfer, it's not the oxygen that gets protonated, but rather it's the carbon, the alpha carbon, that gets protonated to give the 1,5 diketone. All right, so again, we form the enolate first, just like we did in the other carbonyl condensation reactions. Then we get nucleophilic attack, but it is at the beta carbon, so that's very important. And then we'll get a final proton transfer to get our final product. All right, now there's a little bit of, there are some details about the Michael reaction that kind of limit it. This is a very general case, which actually you typically don't see that often. In particular, we're actually somewhat limited in our choice of reactants. And these are the Michael donors. And Michael donors are the things that will form the nucleophile, that will form the enolate. And a good Michael donor should be something that readily forms an enolate. So, something like this, with a pKa of around 20 is not ideal. Something like this, a diketone, is much better. Okay, because this pKa is around 9. And as we saw in the last lecture, if we have a beta diketone, a beta ketoester, this is a beta diketone, a beta ketoester, this pKa is around 11. Let's see, some other Michael donors, R2CuLi. So our R group is going to be the nucleophile. And I'm going to circle the nucleophile. So this is our nucleophile. I'm going to circle the nucleophile in blue here. We could have R, N, R, C, double bond C. We could have an enamine. There's actually a reaction called the Stork-enamine reaction, which is a nice way to make a ketone, diketone. I can't remember. Anyway, I'll get that to you in a future lecture. The thing is that this is the alpha carbon, because this carbon came from the ketone that generated the enamine. So you have to think back to chapter 19. We can take a look at that in class if you'd like. But anyway, this is, enamines are more nucleophilic than enols. So a lot of times it's easier to make an enamine and react that than it is to maybe make an enolate. You don't have to deal with things like LDA and stuff like that. And then we could have other keto species with something electron withdrawing adjacent to the alpha carbon so that it stabilizes the enolate that is formed. But all of these readily form enolates under pretty benign conditions. I mean, sodium hydroxide will turn this into an enolate. And the Gilman reagent you would prepare ahead of time, you wouldn't have or right when you use it is when you prepare it, you wouldn't have base to generate it, let's say. Now, the other part is the Michael acceptor. And these are the electrophiles. And so we could have, all of them will feature some kind of conjugated system, okay, conjugated alkene with some other kind of double bond. So we could have, the simplest one here is this guy there. We could have these could be more substituted. It's kind of nice if they're unhindered like this. Esters will work as well. An amide could work. Conjugated nitrile could work. And even something like a nitro group conjugated with our CC double bond, that could work as well. But in all of these cases, maybe I'll circle it in green. My electrophilic carbon is the beta carbon. So that's where, whoop, let me scoot that up there for you. So that's where our nucleophile is going to add. All right. Now there's one more thing I wanted to talk about in this lecture video, and that is the Robinson annulation. And the Robinson annulation is actually a combination of a Michael and an Aldol reaction. And so our overall reaction would be something like this. So let's take the following example. So we'll have this particular ketone here, and we'll react it with that conjugated ketone and treat that with OH minus and heat, and we will end up with the following species. So we've made a new ring. That's what the word annulation means. It means making a ring. Okay, those are N's. Annulation. There we go. So we do the Michael first. And yes, this is not a great Michael donor. And I'm not going through the full mechanism here. I'm just showing you sort of schematically what happens. So we do the Michael first, and that gives us now a new bond. Boom. And then I've got 1, 2, 3. So 1, 2, 3, double bond O and CH3. And now we still have base present and we heat it up. We will do the aldol next, and it's with a dehydration. So now we have this carbon is going to form the enolate, and it reacts with that carbonyl there, and we end up with new bond, like so. And go ahead and try writing out the mechanism for this. Okay, remember, this is just a schematic here. This is not the actual mechanism, but go ahead and try combining a Michael reaction and then an aldol reaction. I don't know, you might find that it's kind of fun. I actually have a little confession to make, and that is carbonyl condensation reactions are one of the reasons why I am a chemist. I've probably told you how my organic chemistry class that I took fall of my freshman year was really the reason that I ended up majoring in chemistry instead of physics. And it's just my chemistry class was awesome. The professor was Dan Kemp, the late Dan Kemp, and it was just fun to sit there and lecture. And I just love the way that you could do these carbonyl condensation reactions with, and draw out their mechanisms and have and combine them one after another. Do a Michael and then an aldol, or do a reverse aldol and then a Claisen or something. I don't know if you could do that, but do a reverse aldol and then a Michael or something like that, where you could sort of put these back to back and make these much more complex molecules. It was just really, I don't know, I just thought it was really cool, and that kind of inspired me to continue with studying chemistry, and so here I am. Thankfully for you guys, I am here. Anyway, all right, so I'll probably record one more lecture video in the coming days, just going over things to look for, identifying aldol, Claisen, Michael products, etc. And of course, you should definitely look at the practice problems, try some of those, and I'll go over some of them in lecture, in class meeting as well. All right, well, until next time, stay safe out there. Bye now.